Great. So thanks everyone for being here. Today I'm going to talk about an ongoing work on implementing a formally verified proof checker for deep neural network verification. And this is part of my PhD progression assessment as supervised by Katia Komenenskaya, Grant Passmore, and Catherine Stark. So before I talk about the formally verified proof checker for deep neural network verification, first I'll go over why deep neural network need verification, why the DNN verifiers need to produce proof, and why we need to check this proof with a proof checker, and then why this proof checker, it's important that it's formally verified. So to begin with the beginning, neural networks are a class of machine learning algorithms that perform very well in learning patterns from noisy data. Here is an example of a very simple toy neural network represented as a directed graph. So the network is made up of neurons, which are the nodes of the graph, and the inputs are on the left. The output is the Y on the right. The output of each neuron is computed by computing a weighted sum of the output of the upstream neurons, with the weights being in the edges. And then we apply a nonlinear function called the activation function to this weighted sum. Here is the value. So this neural network, as I said, they perform very well for a wide variety of tasks. For instance, image classification, but they're also known to be sensitive to small perturbations. So whether from noise in the data or from malicious outside attacks, called the adversarial attacks. So here we have an example from the MNIST dataset where a small perturbation is applied and a network misclassifies the perturbed image. And as a result, the verification community has worked on tools to guarantee safety properties of neural networks. And these safety properties can take a wide range of nature, but so a popular example is the robustness property, in which inputs within, we want to verify that if the inputs of a network are within a certain safe region, then the output of the network will be in a safe region. And here is an illustration of epsilon ball robustness, which is a formulation of robustness for against adversarial perturbation of images. So as I said, there have been numerous efforts from the verification community to implement DNN verifiers. They can be broadly classified into two categories: constraint-based verifiers, such as Marabou. So these encode networks as first-order logic formulas and the properties as well, and then use linear programming based solving, similar to the one used in SMT solving, to find either a satisfying assignment or prove that no satisfiable assignment exists. So to tell if the property is satisfied by the network or not. And the second broad category is abstraction-based verifiers, which produce an abstraction of a network, so an over-approximation of the network, and then use this over-approximation to reason on it and to check if the property holds or not. In general, abstraction-based verifiers scale better because they reason on a simpler object, since they reason not directly on the network, but on an abstraction. But they are not complete. So for instance, if a verifier concludes that the property doesn't hold on the abstraction, it doesn't necessarily mean that the property doesn't hold on the original network. But so there is this trade-off that we'll find again later between the strength of the safety guarantee and the scalability of the tool. And the three examples that I chose here are state-of-the-art in DNN verifiers. So the abstraction-based one, alpha, beta, crown, and MNBAB are the ones that perform the best at the latest deep neural network competition. So they scale the best. They scale the best on the most benchmarks. compared to Marabou, which didn't scale as well. But I think that it was important to include Marabou because, well, you'll see in a minute that it's the verifier that we'll work with. And it's very much, it's one of the most mature tool. And one way this is evident is that it's being used. So deep neural networks formally verified by Marabou have been used in experiments in by researchers at Boeing on self-driving planes of the same type as this one. An alternative to these two main approaches on DNN verifiers is using interactive theorem provers, or ITP. And the idea is that interactive theorem provers have expressive languages, so we can express more complex properties, and they have other modes of reasoning that allow to prove different properties, safety properties on neural networks. There have been some implementations of neural networks in Coq, and recently, so in my master's work, we investigated using Imandra, which is an industrial theorem prover, to verify directly deep neural networks. And the conclusion of this work was that Imandra, so thanks to the high-level syntax and the reasoning capability of Imandra, which focuses on the reasoning by induction, we were able to formulate interesting properties on neural networks. So for instance, monotonicity, and it was a structural property. So it held not for a specific network, but for all network, regardless of the size that satisfied a certain structure. So it allowed us to express and verify these interesting properties, but we observed that it didn't scale well. And so we were able to, for standard verification properties like robustness, we were limited with a network size. So in this context of DNN verification, there are major questions that are being investigated. So one, as I just mentioned, is which type of properties do we want to prove on neural networks? So is robustness enough, or do we want to prove more complex properties or other properties? One is scalability. It's a major, it's the main focus of the neural network verifiers that are entered, for instance, in the DNN verification competition. With always this trade-off between strength of the safety guarantee and scalability. And this is a major issue because neural networks, as you probably know, are increasing in size. And so now with LLMs and whatnot, there are networks with billions of parameters. Another important aspect is the integration of DNN verification in the verification of larger systems. So neural networks are usually components of larger systems. So if we want to integrate DNN verification, DNN verifiers have to interface somehow with the verification tool of the larger system. And this is very much a challenge that's being investigated, for instance, with the vehicle team in this lab. And finally, there's the question of integrating safety properties in training by converting safety properties in differentiable logic and into the network's loss function. So that's being investigated by So now I'd like to present the work that we've been doing, and it addresses specifically the integration part of the DNN verification challenges. So this is a joint work with Omri Isaac from the Hebrew University of Jerusalem with also our respective supervisors. And I'd like to just note that this is a submission. We submitted a work in progress paper at Lobster. And so if you have any suggestions for the continuation of the work or any questions, stop me at any time. So the question that hails from having deep neural network verifiers is that DNN are exposed to some errors. So for instance, they can have numerical instability. So Gilles Minard showed that they could exploit numerical instability due to the use of floating point arithmetic to generate inputs that violate a safety condition, even if the safety condition has been verified by a DNN verifier. And in addition, DNN verifiers are usually very complex pieces of software. They include a lot of optimizations for scalability, so they're hard to model and to formally verify. And so this vulnerability in a way of DNN verifiers is a barrier to integrating DNN verification into larger verification project, because as I mentioned, the formal verification of the larger system has to be able to interface somehow with the DNN verifier. One solution to this shortcoming is proof production. So the DNN verifier can produce, in addition to its result, a mathematical proof of its results that can be checked automatically by a trusted piece of software that's called the proof checker. And this has been implemented for the Marabou DNN verifier. The proof checker has been implemented in C++, and so it operates on floating point arithmetic, so it has the same limitation that I just mentioned. But it is very scalable. It targeted explicitly scalability. And so that's where we believe that interactive theorem prover can really bring something. Because interactive theorem provers, when they have a high level, they're integrated with a high level programming language interface. They're expressive enough and high level enough that we can implement the proof checking algorithm directly in the interactive theorem prover, and then we can reason directly on this algorithm with the ITP's formal reasoning facilities. So our contribution in this work is to implement an arbitrary precision and formally verifiable proof checker for the Marabou proofs. And for that, we used the Imandra interactive theorem prover, which is an industrial theorem prover, and I will talk more about it in a bit. So before I talk about the proof checker itself, I'll go briefly over the proof production in Marabou, and for that I will talk briefly about the verification technique of Marabou. So as I mentioned, Marabou is a constraint-based DNN verifier. So what it means is that it expresses the neural network and the property in a set of linear and piecewise linear constraints. So the DNNs, one thing that we see here is that the DNN's ReLU node are split between two variables, the B variable and the F variable. The B variable is just the weighted sum of the upstream neurons. And the F variable is the result of applying value to the B variable. So here we can see that the network and the property are translated in a set of linear equations and a set of bounds for each variables. And the ReLU activation functions are translated into piecewise linear constraints. One thing we can note is that the property is actually a negation of the property. So the property that we want to prove is that for all inputs within a certain bound, the network's output is not in the interval 2, 3. And so we pass the negative property to the verifier. And if it finds satisfiable assignment, so if it returns sat, it means that an input violating the property exists. If it returns unsat, so there is no satisfiable assignment, then it means that the property holds. So once we have this query with linear and piecewise linear constraints, this is turned into a linear programming system with a tableau, which represents the equations E1, E2, and E3. And the bounds vectors are initiated, U for upper bound and L for lower bounds. And then, so this is a classic linear programming system. And then we know the simplex algorithm, which can solve this type of problems. And so the simplex tries to find a satisfying assignment for the variables in X, such that the assignment satisfies the constraint expressed by the tableau, and they're within the bounds that we defined. One thing to note for this example is that some of the bounds were set arbitrarily. So what's Marabou? So this simplex method works for when there are only linear constraints, but so as we just saw, here we have piecewise linear constraints on top. So Marabou for that uses the reluplex algorithm, which is an adaptation of the simplex for neural network verification with piecewise linear activation function. So what the reluplex algorithm does is try to to perform simplex to solve the linear equations, and then try to massage the results to satisfy the ReLU constraints. If this is not possible, it splits the piecewise linear constraint. So it creates two subqueries which represent a piecewise linear constraint. And then it tries to use the simplex again on the newly generated subqueries. So here, for instance, we see that we split on the V3 neuron. On the left side, it's the case where the input variable of the V3 neuron is positive. So the output will be equal to the input as per the definition of ReLU. And on the other side is when the input is negative. And so the reluplex algorithm also performs the dynamic bounds tightening to reduce the search space dynamically. And in the end, if all the leaves of this search tree have an answer from the simplex algorithm, then the query has an answer. And in particular, if all the leaves are unset, then the query as a whole is unset. The proof tree, or the proof that's generated for the Marabou verifier, reflects this tree structure. So it's the proof is constituted of the tableau, the initial tableau that I showed, as well as the lower bounds and upper bounds vector, which are we call the ground bounds. It's the bounds that we start with. And then it has the same tree with that contains in each node an explanation of the tightening if some dynamic bound tightening has been performed. And in the leaves, a vector that explains the contradiction that leads the simplex to conclude the unsatisfiability. This is for a non-sat query, by the way, because we see that all the leaves have an explanation for unsatisfiability in the form of a vector. So this is a non-sat tree. And we'll see in a second where these explanations come from. So in Omri Isaac's previous paper, so where he implemented the proof production, he proved that in the unset case, in the configuration when we have the tableau A and the lower bound, upper bound for X, there exists a vector which gives a linear combination of the rows of the tableau. And for this linear combination, the upper bound of this linear combination and the bounded X variables is strictly negative. And if a solution to the constraint existed, the X would be within the bounds, and for any linear combination of the tableau rows, the result would be null. So if the upper bound is negative, it's a contradiction, and so this vector W is a proof of the constraint's unsatisfiability. And it was also showed that the vectors can be constructed while performing the simplex algorithm. So when we have, and sorry, I forgot to mention that there exists the same, there exists a similar theorem that states that there exists a vector that explains the bounds of a dynamic tightening from the ground bounds and from the initial tableau of the query. So the proof checking algorithm at a very high level what it does eventually is that it traverses the tree. For each node, it will check that if there is a dynamic bound tightening, it will check that the dynamic bound tightening is valid, that it corresponds to an existing ReLU constraint, and that's the bound of the explaining variable. So here the explaining variable would be B3. So this is a tightening from to say that the upper bound of F3 would be 1 because the upper bound of B3 is 1. And so this vector explains the upper bound of the explaining variable. So the proof checker checks that all this is valid and corresponds to valid constraints. And then it will traverse the tree, and in each node with an unsatisfiability explanation vector, it will compute first the linear combination of the tableau rows that is indicated by the explanation vector, verify that it's the upper bound of the underlying linear combination with the variable is negative. And if this upper bound is indeed negative, then the explanation is considered as valid. And so once the proof checker has traversed all the tree and checked all the nodes and all the leaves, we can conclude that the proof is indeed correct. That was a bit heavy. So are there any questions on the proof checking or proof production? I'm not going too much into detail in the proof production. The idea is really to give you an understanding of what the proof checking does and what form the proof of correctness has. If there's no question, I'll go on. About the Imandra implementation. So first, I want to explain why we used the Imandra theorem prover. So the idea, as I mentioned earlier, of using an interactive theorem prover is that we are able to minimize the verification gap. So by implementing our proof checking algorithm directly in an ITP, we reduce we suppress the discrepancy that can exist between a deployed model and its verified abstraction. So because Imandra has a logic based on a pure OCaml or on a pure subset of OCaml, and it has a facility to extract the verified code into native OCaml. So it gives us access to the optimizations, for instance, of a native OCaml compiler. So it means that the code that we verify and the code that we deploy is exactly the same code. It has the same semantics and everything. And in particular, it has arbitrary precision with arithmetic, which allows us to avoid the problem of numeric instability due to floating point arithmetic, for instance. So the biggest part of implementing this proof checker in Imandra was to, in a way, adapt the proof checker that already existed in C++ into a pure functional language that comes with its own software engineering challenges, especially as Imandra is also a restricted subset of OCaml. So that came with a number of engineering challenges, but one of the direct benefits that we get from it, for instance, is that the correctness of the proof tree and the proof nodes is checked during type checking. So we implemented a proof tree type with different constructors for nodal leaves, and so where the C++ implementation had to do runtime call to some function that checked the validity of the tree or the structure of the nodes. This is performed at during type checking. So that's a nice benefit of using a functional programming language. Then Imandra also has arbitrary precision arithmetic. So here we can see just a really toy example of maintaining the precision of a simple arithmetic operation on a pi approximated to the 30th decimal, I think. But so we see that the real numbers are presented as arbitrary precision integers, and so the precision is maintained. And this is done using a native OCaml library for arbitrary precision arithmetic. which itself is based on a GNU library for multiple precision arithmetic with its own set of optimizations. And so that's really an advantage of using Imandra, is that with virtually no overhead, because this is the native way of handling real numbers by Imandra, we get arbitrary precision with a mature implementation and optimized implementation. One design choice that was that we found to be important is the choice of a data structure representation. So from the explanation of the proof checking algorithm, you see that there was quite a lot of matrix, arithmetic, and vectors. So choosing how to represent vectors and matrices came as an important choice. From previous experience of using Imandra for DNN verification, we saw that some data structures were better suited for performance, but posed problems for when we try to reason or for verification, and the other way around. And even we can see here, just without going in detail into the code, we can see that if we use the native lists, so with the classic inductive list definitions from programming languages, we have to do some pattern matching in case of list size mismatch. Whereas when we use sparse lists, expressed as binary trees, they're defined as total functions. So this question of list size mismatch does not occur, and we can also express the computation more succinctly using a folding for the list. So here, this is a refinement of the initial representation that I showed, where the C++ implementation favors scalability, ours favors trust at the expense of some scalability. We have some variation within that. So it was our initial idea that the sparse list representation, since it gives quicker access to random elements in the list, would have a better scalability. We'll see in a moment that it's not quite there yet, but that's the idea. And when we first implemented the full proof checking algorithm, we noticed that it would often very quickly go over the timeout that we had set. So we also implemented a second mode of verification, which is orthogonal to the data type choice, which allows to only check the leaves and not the nodes, and so increase slightly the proof checking time. So we have a preliminary evaluation. It's not exhaustive, but this is the evaluation on proof checking for some problems from the HWU benchmark of neural network verification. So we can see on the left the time in seconds of the C++ verifiers. And we can see that the Imandra verifiers are always slower by quite a lot. Here we can see that the sparse vectors for the full verification are actually much slower than the native list implementation. So that gave us a good insight on how to further optimize the code. But we can see that in the best case for the full verification, so with native lists, it's a linear overhead compared to the C++ original implementation. The time is about 150 times slower than for the C++ implementation. This was expected because we know that from experience that the verified code decreases scalability. Now that we went over the implementation, I'll talk briefly about the specification of correctness for the proof checking algorithm. So we formally defined the correctness specification for the checking the contradiction in the leaves of the proof tree. And so this ties back to the theorem that I showed before. So we want to show that for contradiction vectors with the tableau and the variable vector x that bounded by L and U, if the upper bound of the linear combination indicated by the W vector is negative, then X cannot satisfy the constraint of the linear programming query. And this is implemented in Imandra as shown here. So the parameters of the theorem function are all implicitly universally quantified. And this is the formulation of the theorem, but it's not yet approved the theorem in Imandra. In order to prove this theorem, we've started to verify some arithmetic property of our implementation. So here, for instance, properties of the dot product operation on vectors, and we can see that the way that the interactivity works in Imandra is that we define low-level lemmas. And once these lemmas have been accepted, they're added to Imandra's logic and or theory, and then they can be reused to prove higher level lemma, either automatically or by using annotations such as here. The implementation. So to conclude on this work, we try to overcome the problem that the existing proof checker for Marabou proofs was lacking formal verification and was still exposed to numerical instability. So what we did was implement a formally verifiable and RB precision proof checker in Imandra. And we expected some trade-off between scalability and strength of trust, but we're happy to observe that it's only a linear overhead that's added. And so as immediate future work, our goal is to optimize the algorithm. As I stressed, there are some obvious avenues for optimization, but also we want to look into implementing more efficient sparse lists, and then obviously finishing the verification of the proof checking algorithm. So proving the full, all the steps of the proof checking algorithm. And one thing that we also want to do is to identify cases where the certified proof checker makes an observable difference, or like gives a different output than the non-verified C++ proof checker, to make obvious the benefit of having a certified proof checker. As this is a PhD progression talk, I'll mention briefly other works that I've done this year and future plans for the future. So the general motivation for this PhD is the formal verification of deep neural networks and the benefit that interactive theorem provers can have in this. So as I mentioned, it was the continuation of exploring using Imandra as a DNN verifier directly, but so then we, after seeing the limitations, we try to explore alternative use of ITPs for DNN verification. So in order to get a deeper understanding of ITPs, I implemented proof of monotonicity for a small class of neural networks, both in Coq and Imandra. And then the main work was on this Marabou proof checker project. So after in immediate plans, I plan to finish the Marabou proof checker project, finish the verification and submit the results to a conference. And a new research avenue that we've recently opened is a similarity measurement for a compressed neural network. I'll talk briefly about it. And if you have any feedback or ideas on this, since this is also an early research investigation, I'd be very happy to hear your thoughts. So the problem is that deep neural networks need a lot of resources, especially with recent developments in large language models. So there exists some compression techniques that reduce the size of neural networks while ideally keeping their performance intact, such as quantization, distillation, or pruning. And the question that we want to investigate is, how do we measure the similarity of the original and the compressed models, or their divergence? So for now, the main mean of measuring this is using just the performance metric. We just want the compressed model to be as performant as the original one. Then there has been some investigation in strict equivalence checking. So encoding equivalence as a verification property and verifying it using the same type of verification tool that I mentioned before. Then there was also, I found using the Euclidean distance between the weights of the networks. But so the idea is to investigate other formal verification inspired techniques, mostly based on abstract interpretation, to study similarity or differences between original and compressed model. And why not generate counterexamples, so inputs that make the compressed and original models behave differently and gain more insight in the difference from these counterexamples. So yeah, that's me. And as I said, I'd be happy to take your questions or suggestions on these topics. Thank you. Yep.
Quick question, but when you were talking about the arbitrary precision and so on, so you said it uses the native library in Camelfish, then uses the native library there, and so on and so on. So what do you, and you're verifying things, what do you trust here? Because I don't think that that this implementation stack has been verified. So you're relying on the fact that this is these are rational numbers correctly, or is that actually verified?
No, that's a good question. I don't know if it's verified. I'd assume not, but it's a good. It's an important question. I mean, it's also something that came up, you know, when just when I was preparing this talk of, you know, having to explain that the verifier verifies the network, the proof justifies the result of the verifier, the proof checker assumes, and it's a bit of a problem of turtle all the way down, right? Like, at which point do you trust what? And when wondering that, I came to the conclusion that we trust Imandra, but your question raises an interesting point of, even in a interactive theorem prover, which is on principle trustable, to what degree do we trust? But actually, I actually don't know. I need to check, like, what's the correctness guarantee for this arbitrary precision arithmetic library?
This is something that from what I've looked at in Imandra, and this is the kind of a problem of industrial provers in a way. It feels, maybe I'm wrong, but it feels like Imandra cuts corners here and there and says we're going to use native implementation of this and that and the other thing and so on. And all of these native implementations are actually just trusted.
I think if you can't trust GMP, you can't trust anything on your machine.
And just as a
it's in particular case of GMP, of course, right? Because like if there's one thing that's actually tested to the death and then some, it's probably GMP.
Yes, but there's a real difference between tested and verified.
Yeah, for sure.
And if you're running a verification program, it is good to know what is it that we are implicitly trusting.
Yeah,
and make it more explicit.
Yeah, that's a good point. That would actually be a good engineering problem of formally verifying.
It might be an issue of the Imandra documentation, right? Does the Imandra project list what are the unverified things it relies on?
Yeah, I need to check on that. That's
you have a direct line to.
Yeah. I can ask. It's a good point. For that. There's a question online.
Raise your hand.
Yeah, if you want to ask a question, Katia.
Yeah, Remi, first of all, thanks for a very well prepared talk. It was very well done. I wanted to ask a little bit from Imandra perspective. Have you had a chance to ask Imandra people where they need neural nets verified? So is there any, I mean, there is some library for neural nets in Imandra. Do they ever say, okay, so we use these neural nets in this financial application and we would like to verify them or include neural net verification in the larger system? Because if there was such a case, then we could play the same role as vehicle plays. Vehicle first verifies low-level stuff and then passes higher-level verification to Agda. Same stuff could be done here. You have low-level verification neural networks in vehicle, and then Imandra does meta-reasoning on this. So it's actually two questions then. Have you heard from Imandra team whether they're interested in neural net verification for their industrial projects? And then have you thought of connecting Imandra to vehicle?
So from what I understood from my discussions with Imandra people, they don't have for the moment verification projects of systems with neural networks in them. But then we did mention integrate or interfacing Veiko and Imandra together. And that's something that Grant, for instance, was very interested in. And there is a plugin system in Imandra where you can implement, I want to say strategy, but I'm not sure if it's the right term, but you can call specific strategies for specific, to call specific solvers. So for instance, there is this option to call a custom SAT solver instead of the default reasoning mode. And so we could imagine, for instance, having such a strategy defined for verifying a neural network, call Veiko on this network and then get the answer from Veiko and then use it for Imandra proofs. That's something that we discussed, and that's definitely doable. And that we're interested in.
Okay, thank you.
Great question. Yes.
So you mentioned lemmas a couple of times towards the end of the talk. So you drive the interaction through lemmas that you provide. It's like the more and more paradigm.
Yes.
You also had a table earlier where you had lemmas listed. You didn't talk about what those columns meant.
Do you mean this or an earlier table?
If you go earlier, there's a table of results there.
Oh, sorry. Yeah. So that's confusing terminology on my part. So the lemmas that we mentioned here are the theory lemmas that are used for the dynamic bound tightenings in the reluplex algorithm. So it's unrelated, and it just means that in the columns with no lemmas indicated, we don't check the bound tightening performed in the tree correspond to known bound lemmas. So when we implement the proof checker, we define a number of lemmas that can be used for bound tightening. And so that's where the confusion comes from. That's actually something that we've been struggling with and trying to find like a better terminology for these lemmas.
I had another question.
Yeah.
So right back at the start, you gave a nice presentation about the constraint-based approach to the abstraction. Abstraction gives you the ability to tackle larger problems because you're abstracting the detail, but then you run the risk of missing issues. Yes, missing bugs, basically.
So I think the main problem for abstraction is that I'm trying to think if you can have false positives. But I know one big problem is that it gives false negatives, or it can give inconclusive results in case of negatives, yes.
And you don't know that, do you?
Yeah, well, I think it's hard to know if the result comes negative. You cannot, you can try to refine your abstraction to up to a point, but
so that was at the heart of my question. So it's a question that's bigger than your PhD, I think. Okay. It's a general question because predicate abstraction is well used in formal methods where you build the abstraction and you hit it with the model checker. But you can, if you find that you're getting a false result, you kind of reduce the abstraction. The improving quite often comes into play there. I'm just wondering if there was an analogy here that people could follow, where instead of, I presume they're picking one particular abstraction.
Yeah, I mean, yeah, when the one that I'm aware of, they use one abstraction technique, and then so it's actually implemented on top of Marabou, so it merges the abstraction and then constraint solving. For instance, they merge nodes with similar weights, reduce the network size, and then like split them again if the abstraction is not inclusive.
So is there any link to that and compression that you mentioned towards the end as a future challenge?
That's a good question. I'll have to think on it, but yeah, that's an interesting idea. So pruning, in a way, is a form of abstraction because you remove nodes with weights that are under a certain threshold. So yeah, I wonder if this could be investigated.
If you enjoyed using Imandra?
So the learning curve was definitely quite steep. I can say that. But I mean, first I was lucky enough to have direct access to the people who wrote it. So that's really useful when learning a new piece of software. And when doing the verification, I think we've been now that we have good grasp, or that I have a good grasp on the way it works and the way I can interact with it by proving the small lemmas and then looking at Imandra's failed proof attempts to figure out which new lemmas to try and prove. I think it's an enjoyable tool to use. And yeah, also I had a bit of experience in functional programming, so that definitely helped.
Thanks.
Thank you. Any other questions? I guess